TensorFlow is a powerful open-source machine learning and deep learning framework developed by Google, offering a versatile ecosystem for building and deploying machine learning models efficiently. At its core, TensorFlow revolves around tensors, multidimensional arrays representing data, which flow through computational graphs where mathematical operations are performed to train and infer from machine learning models. This framework provides developers with a wide range of tools and libraries for tasks such as data pre-processing, model building, training, evaluation, and deployment. TensorFlow's flexibility and scalability make it suitable for various applications, including computer vision, natural language processing, and reinforcement learning. It allows developers to experiment with different machine learning algorithms, architectures, and techniques, accelerating the development and deployment of AI solutions. TensorFlow, an open-source framework developed by Google, has become the go-to solution for both developing and deploying machine learning models, particularly deep learning models. Its rich ecosystem of tools, libraries, and community resources empowers developers and researchers to tackle a wide range of machine learning tasks effectively. TensorFlow's flexibility lies in its architecture, which accommodates both high-level APIs like Keras for rapid prototyping and low-level APIs for fine-grained control over model construction. Additionally, TensorFlow optimizes computations efficiently, leveraging hardware accelerators such as GPUs and TPUs to enhance performance. Its extensive library ecosystem includes tools for data pre-processing, model evaluation, and deployment, exemplified by the tf.data API for streamlined data input pipelines and TensorFlow serving for seamless model deployment and serving. These features collectively make TensorFlow an indispensable tool for practitioners across various domains of machine learning and artificial intelligence. TensorFlow operates on three key concepts: tensors, computational graphs, and sessions. Tensors are the fundamental units of data in TensorFlow, representing multidimensional arrays that flow through the computational graph. For example, a tensor could represent an image, a piece of text, or numerical data. Computational graphs are representations of mathematical operations as nodes, and the flow of tensors between them as edges. They define the sequence of computations that TensorFlow will execute. Sessions are execution environments in which TensorFlow operations and tensors are evaluated. For instance, to perform operations on tensors, one must run them within a session. Here's a simple example. In TensorFlow, we can create a tensor representing a 2x2 matrix, define a computational graph to multiply it by itself, and then execute this graph within a session to compute the result. This trio of tensors, computational graphs, and sessions forms the core foundation of TensorFlow, facilitating the development and execution of machine learning models. Tensors serve as the fundamental building blocks in TensorFlow, enabling the representation of data and computations within the framework. They are multidimensional arrays that generalize the concept of matrices to higher dimensions, accommodating a wide range of data types and structures. In TensorFlow, tensors can have an arbitrary number of dimensions, making them versatile for handling diverse data, including scalars, vectors, matrices, images, and sequences. For instance, tensors can represent pixel values in images, time series data in audio signals, or feature vectors in machine learning models. TensorFlow provides various functions for creating and manipulating tensors, such as tf.constant, tf.variable, and operations like addition, multiplication, and reshaping. Tensors are integral to the efficiency and flexibility of TensorFlow, enabling optimized computations on hardware accelerators like GPUs and TPUs, and forming the foundation for deep learning models, where operations on multidimensional data are common. Examples of tensors in TensorFlow include constants, variables, placeholders, and the outputs of operations performed within a computational graph. Through tensors, TensorFlow facilitates the development and execution of complex machine learning models, making it a powerful framework for numerical computing tasks. The TensorFlow computational graph serves as the backbone of TensorFlow, representing the sequence of operations and data flow in a TensorFlow program. It is a directed graph where nodes correspond to operations, ops, and edges represent the flow of data, tensors, between these operations. By defining the structure of the graph and specifying the operations to be performed, developers can create complex computational workflows for various machine learning tasks. For instance, in a simple computational graph, placeholders are used to feed input data, operations perform computations on this data, and output nodes produce the final results. Running the computational graph within a TensorFlow session enables the execution of these operations, allowing for the efficient evaluation of machine learning models. Through examples like building a graph to perform arithmetic operations or defining a neural network architecture, developers harness the power of TensorFlow's computational graph to create and execute sophisticated machine learning algorithms efficiently and effectively. In the provided code snippet, we engage with TensorFlow to construct and execute a computational graph. Firstly, we build the graph by defining placeholders x and y to represent input data. Subsequently, we define operations within the graph such as addition, add_op, and multiplication, mal_op. These operations act upon the input placeholders to generate desired outcomes. An additional operation, output, combines the results of the previously defined operations. Following graph construction, we proceed to execute the graph within a TensorFlow session. Utilizing the run method within the session, we evaluate the output node, supplying input values for the placeholders via a feed dictionary, feed_dict. This enables TensorFlow to carry out the computations defined in the graph and produce the final result. Through this structured approach, we harness the capabilities of TensorFlow to create and execute computational graphs efficiently, facilitating various machine learning and numerical computing tasks. Keras is a high-level neural network API written in Python, which simplifies the process of building, training, and deploying deep learning models. It offers an intuitive and user-friendly interface that abstracts away many of the complexities associated with neural network implementation. Through the use of predefined layers, activations, optimizers, loss functions, and utilities, developers can quickly assemble powerful neural networks with minimal code. By importing modules from TensorFlow.keras, such as layers and models, developers can access a variety of building blocks for constructing models. For instance, the models.sequential function enables the creation of a sequential model by stacking layers, such as layers.dense, which defines a fully connected layer with the ReLU activation function. Additionally, with just a few lines of code, models can be compiled using the compile method, specifying the optimizer and loss function to be used during training, such as Adam for the optimizer and sparse categorical cross-entropy for the loss function. This streamlined approach to deep learning development provided by Keras accelerates the prototyping and experimentation process, empowering developers to focus more on model architecture and experimentation rather than implementation details. Let us consider a simple illustration of how TensorFlow can be used to create and train neural networks for image classification tasks. However, TensorFlow's capabilities extend far beyond this, encompassing a wide range of machine learning tasks and applications. In this example, we are utilizing TensorFlow to build and train a convolutional neural network, CNN, for image classification. First, we load the CFR10 dataset, consisting of 60,000 TOS 32 pixel images belonging to 10 different classes. After pre-processing the data by scaling pixel values to the range 0, Menki Fun, we construct a CNN using Tensorflow's high-level Keras API. The model architecture comprises convolutional layers with ReLU activation, followed by max pooling layers, concluding with fully connected layers. We compile the model with the Adam optimizer and sparse categorical cross-entropy loss function. Subsequently, we train the model on the training data for 10 epochs, validating its performance on a separate test set. Finally, we evaluate the trained model's accuracy on the test set, showcasing TensorFlow's capability to effortlessly develop and train complex neural network models for practical tasks like image classification. Completing the TensorFlow course is a significant milestone, symbolizing the journey of mastering one of the most powerful and versatile deep learning frameworks available today. Throughout this course, you've immersed yourself in the intricacies of TensorFlow, gaining a profound understanding of its capabilities and applications across various domains of machine learning and artificial intelligence. You've explored TensorFlow's rich ecosystem, delving into its robust tools and libraries. However, true mastery of TensorFlow extends beyond theoretical knowledge to practical implementation. Hands-on experience plays a pivotal role in solidifying your understanding and enhancing your proficiency with the framework. Therefore, we encourage you to continue honing your skills through hands-on practice, experimenting with different techniques, and applying TensorFlow to solve real-world problems.